This is part two, the second part of our lecture on modeling specific responses by the immune system. We are now more familiar with some of the special forces of the immune system, the CD4 T cells, the CD8 T cells, B cells, and antibodies. And so we're also a little more familiar with antigens and epitopes. So let's review some mathematical equations that account for these responses by the immune system. We're going to write sets of equations that are in groups of two, where we have the population of virus interacting with a population of immune cells. And specifically, what we're going to consider here, it's something that perhaps is more is easy to find an example with the influenza viruses. Every year we have a season called the flu season. It starts in October and it runs October, November, December, all the way into the next calendar year through April. The reason why, and people get the flu shot, people get vaccinated, uh, get some level of protection against influenza viruses. But what happens is that every season we have viruses circulating. If we were going to have this year the same viruses of influenza that circulated last year, then we really wouldn't need the flu shot because of that ability our immune system has to maintain some memory. What happens is that the viruses are influenza viruses, but they are not identical clones to each other. And the viruses that circulate from year to year have a degree of similarity, but also are, if you will, random mutations. They undergo a process in which, when they make copies of themselves, they're not really cloning or making identical copies. And this is precisely to deviate from the many possible mechanisms the immune system has to recognize them, right? So the viruses are trying to make copies, but adding variability to camouflage themselves and kind of get by. Getting, the viruses want to get away with crime. And remember, viruses are the unwanted, the most unwanted. Our immune system is fighting them off. They want to kick them out of our body. So, there are so-called variations of virus that are going to be considered mutations of virus. So we can call them mutants. And for each version of the virus, there will be deployment of immune responses that will go after that specific, um, uh, in this context, these mutants, you can also call them strains or strands of virus, strains, strands, but we're going to call them mutants. So we're going to consider there are n mutants, and the label we use here for these mutations of viruses, we're going to have some label with index I, and there are 1, 2, 3, all the way through n. So for each value of I, we're going to have V sub I, which denotes the size of the mutant I at time t, and X sub I of t, is the magnitude of the immune cells, the size of the cells of the immune system that are responding to that specific mutant or mutation of the virus. So these are very broad equations, and we're kind of putting together in this class X sub I all possible responses here, which, you may argue this may or may not be the best. The model is broad still, but is simple equations, simplest model first, right? That's it's an okay rule to follow. So the terms here are familiar. The growth of the population V sub I is proportional, stimulated proportional to the size of that population, and the encounters between V sub I and X sub I are going to be detrimental to the population size of that mutant I. At the same time, the more of those, the larger that size is, then that is going to stimulate the deployment of the immune system with cells X sub I. So this source term, this gain here for X sub I is proportional to the size of how many mutants are in circulation. And then there is a term B sub I, which is some type of decay. So here we have the following: the absence of immune responses, right? So if this term were zero, then the viral growth is basically growing exponentially at a rate r times v, and immune responses are stimulated in proportion to the abundance of virus. This term, which is very similar to some of the terms we had seen before, law of mass action, if you will, those are um, the rate at which the virus is being cleared out of the body from by the immune system. Okay, and then this rate B sub I, you can consider that as some kind of natural decay. Okay, so what happens if n is 2? What happens if we consider the mathematical model for which we have two mutants? Okay, and I'm gonna show you the equations, what they look like. We're going to run a simulation, compute a numerical solution, and then as an exercise, this would be a good exercise, then you assume n equals 3 or n equals 4, and then you can code those equations. So when there are two mutants, we write here v1x1, v2x2. These are the equations according to our previous slide, right? So in this case, we have four state variables, four differential equations, and we have parameters R1, P1, C1, B1, right? For each set of two, for each interaction between virus and immune system, we have four parameters. We have two sets of two, so we have in total 8 parameters. So let's code these equations, and let's see what the numerical solutions look like. So here I have our studio, and what you're seeing is the script that I'm using to compute numerical solutions of this model with two mutants. Okay, so it's not too long. This script basically has 65 lines of code. Okay, let's revisit section by section here of the script. This part, you have to install ahead of time DE-solve. Okay, so we are calling that library DE-solve on graphics because we're going to plot some of those solutions. The next portion of this code that's important is what is in this function. This function contains the equations for this shouldn't be for the simple model virus dynamics with antigenic variation. All right. So maybe just say mol, whatever. So that's what goes between lines 6 through 22. Okay, and so first I define three input arguments for this function. One of those arguments is a vector that stores the constants that are the parameters, and then I have t and z. Typically we use x, but here I'm using z to denote the state variable. There are four state variables, therefore four derivatives which are stored in this variable. Here I initialize that with zeros, and then I write the equations. I'm following the order z1 for v1, z2 for x1, z3 for v2, and z4 for x2. Okay, so after that function is defined, we can set values for the initial conditions. In this case, I'm setting all the initial conditions to the same value, which is really, really small, 10 to the minus 5. And then I choose parameters. I choose a lot of these parameters to be set to the same value. For example, P1 is 2 and P2 is also 2. And then I choose C1 to be zero point 0.1 and C2 also to be zero point 0.1, and B1 and B2 also are set to the same value of zero point 0.1. The main difference is R1 is set to 0.5 or 1 half, and R2 is set equal to 1. Okay, so I store those values into this variable. I define time points here between 0 and 300 and steps of 10 to the minus 2, and this is the big moment. We call L soda, and this is what computes the numerical solutions. So let me select everything, and I will hit run and show you what we get. So after I execute that code, LSOTA provides us with numerical solutions for the mutants of virus and for the specific responses for these viruses. And that's what we have um, that's what we have plotted here in this figure. I grouped them in two groups so that in the same figure we can see for example V1 and X1. So here in gray is the virus, the size of the virus, and in blue you can see the immune response. And so there is some damp oscillation behavior here, but importantly what you see is that these oscillations is one in response to the other, right? So when the amount of virus spikes here to a really large value, at the point in which this is already too much, that deploys or undergoes an implies an activation on the immune system, and somehow the immune system peaks, and that is related to the decline of virus, and then the virus goes to a very very low level, grows back up, and at some point when it's growing, that also stimulates another response by the immune system, and so they kind of keep each other in check, and eventually they're settling here to some positive equilibrium level. So that is a pattern we have for one mutant and one specific response, and here is the simulation or the numerical solution for the other mutant with the other specific response. What we can see, while they're not identical, they are very very similar. Okay, and this concludes our lecture on a mathematical model that includes antigenic variation.